If the deep ocean is full of sound, waves, ships, animals, rain, your own machinery, how does a submarine actually see with that sound without getting lost in the noise? The answer is sonar. But not the Hollywood kind with neat, clean pings. The real thing is messier, more statistical, and much more patient. The ocean kills light quickly, but carries sound surprisingly far. And submarines pay a high price for speed, because cavitation can turn their own propellers into loud, boiling noise. In this episode, we combine both ideas. The word sonar stands for sound, navigation, and ranging. In principle, it's simple. You either listen to the sound the world already makes, or you send out a sound pulse and listen for the echo. Those two modes define almost everything in underwater sensing: passive sonar and active sonar. One-sentence example. A submarine on patrol will usually use passive sonar to stay hidden, and only risk active sonar if it must see something clearly and can afford to be heard. At first, passive sonar sounds easy. Just listen. But the ocean is not a quiet room. It's more like a crowded cafe where everyone talks at once, and you're trying to recognize one voice across the room. Let's start with passive sonar. Imagine you're wearing headphones in a dark room. You can't see anything, but you can hear a car pass outside, a fridge hum in the kitchen, and someone walking down the hallway. Each sound is a pattern in time and frequency. Submarines do something similar, but with far more detail. Along their hulls and in long-towed arrays, they have lines of hydrophones, underwater microphones that convert pressure changes into electrical signals. Because these sensors are spread out over distance, the system can tell what direction sound is coming from, sometimes how fast the source is moving, and with enough experience, even what kind of ship or submarine it is. How? By its acoustic signature. One-sentence example. A particular class of submarine can often be recognized by the exact spacing of its propeller blade tones and the hum of its machinery, much like you recognize a friend's voice. Engines hum, gears whine, propellers create low-frequency thumps and higher overtones, pumps and fans add their own textures. All of these add up to a pattern. Sonar operators learn to recognize those patterns in two main ways: as a broadband sound, a kind of overall noise color, and as narrowband tones, distinct lines in the frequency spectrum. One-sentence example. A propeller's overall rumble is broadband, while the steady tonal blade rate that shows up as a sharp line in the spectrum is narrowband. Broadband helps you notice that something is there. Narrowband helps you figure out what that something is. But the ocean doesn't make this easy. There is always background noise, waves breaking on distant shores, wind and rain on the surface, small snapping organisms, other ships far away. All of that adds up to what sonar folk simply call ambient noise. The problem becomes a basic but powerful idea: signal-to-noise ratio, SNR. One-sentence example. If a submarine's propeller is only slightly louder than the surrounding sea noise, it may be almost impossible to pick out at long distance. At long range, even loud ships can melt into the background. At close range, even a quiet machine can suddenly stand out. So passive sonar is not just listening, it is pattern recognition under poor SNR. It asks, is that faint low-frequency thump just distant waves or a ship's propeller? Is that tone a natural resonance in the sea or a specific gearbox frequency I know from a catalogue? And yes, there are catalogues. Databases of known acoustic signatures built over years of recording and analysis. But you rarely get a clean print. You get a smudged version, partly overwritten by noise, stretched and shifted by motion and water conditions. It's a bit like recognizing a song from a few notes played through a wall. Now to active sonar. This is the kind most people imagine when they hear ping. You send a short pulse of sound into the water, wait for it to bounce off a target, and listen for the echo. From the time delay, you estimate distance. From the angle where the echo is strongest, you infer direction. One sentence example. If a sonar pulse takes 1 second to go out and back in water, the object is roughly 750 meters away, because sound travels around 1,500 meters per second in seawater. Active sonar can be very effective, especially against quiet or non-cooperative targets. But it comes with a price. If you ping, everyone within range knows you are there. Unlike light, which mostly goes in straight lines, sound in the ocean can bend, reflect, and follow complex paths. That means your pulse might travel into areas you didn't intend, reflect off layers or boundaries, and be heard by ears you didn't plan to talk to. So active sonar is like shining a bright flashlight in a dark room. You see more, but you also tell others where to look. In peacetime, ships and submarines may use active sonar more freely, for navigation, depth checks, or search and rescue. In tense situations, a submarine will often prefer passive mode and only risk active pings if the tactical situation demands it. Movies love active sonar because it's cinematic. A single, clean ping, a glowing line on a screen, and a target appears neatly in range. Real displays are rarely that neat. The ocean is full of reflections. Sound can bounce off the surface, off the seafloor, off layers of water at different temperatures. Sometimes it even gets trapped in channels and comes back in places you don't expect. A simple model of sound going out and straight back is often only a rough approximation. Sonar operators have to learn to deal with multiple echoes from the same target, false returns from the bottom or other objects, and shadow zones, regions where sound does not easily reach. One sentence example. A submarine hiding in an acoustic shadow behind a seamount may be much harder to detect, even with active sonar. In passive sonar, shadows appear where noise from a source cannot travel easily. In active sonar, shadows appear where your own pulses can't reach, or where the echoes return along paths your sensors do not cover well. Either way, sonar is not a perfect flashlight. It's more like trying to understand a room by clapping your hands and listening to the echoes while someone runs a vacuum cleaner in the background. This brings us to the human part. In many navies, sonar operators spend years training their ears and their pattern recognition. They work with waterfall displays, time versus frequency plots where tones appear as lines and noise as clouds. They learn to spot the slow, regular lines of propeller blade rates, the sharp spikes of transient sounds, doors slamming, tools dropping, sudden machinery starts, and the subtle drifts in frequency that indicate motion. One sentence example. A sudden transient clank from inside a submarine may reveal its presence against a background of otherwise steady ocean noise. Machines can help, but unlike in movies, there is rarely a single magic button that says, "Submarine here." You have hypotheses, probabilities, hints. You might think, this pattern looks like a merchant ship at medium range. There's a faint low-frequency line drifting, maybe a distant submarine changing course. That broadband noise spike could be cavitation from a maneuver. Sonar is as much interpretation as it is measurement. Let's connect this back to what we've already seen in Silent Oceans. From episode 1, we know that sound travels better than light underwater, especially at lower frequencies. From episode 2, we know that cavitation creates broadband noise that submarines desperately want to avoid. Passive sonar cares about all those details. It listens for the low-frequency hums that travel far, the higher-frequency hiss that may stay more local, and the sudden appearance of noise that wasn't there a moment ago. A submarine that suddenly accelerates past its silent speed might light up the ocean in passive sonar, even if its active sonar stays off. Active sonar, in turn, uses the same medium, water, but injects its own energy into it. It has to fight the same problems of transmission loss, noise, and multipath propagation, only from the other side. In both cases, the core question is the same. How do you get a usable signal out of a medium that is constantly writing its own noise? There is one more dimension to sonar that movies often ignore: time. Detection is rarely a single moment. It's more often an accumulation. You might hear a faint pattern, then it shifts slightly. Then you correlate it with expected shipping routes. Then you notice it doesn't match any known merchant profile. Over minutes, sometimes hours, the picture sharpens. Bearings change in a way that suggests a certain speed and course. The spectrum shows lines at frequencies you associate with a known design. Occasional transients confirm that the source is mechanical, not natural. Only then does a contact transform from unknown noise to probable submarine in the minds of the crew. In that sense, sonar is not just a sensor. It is a discipline of patient listening. By the end of this episode, you can see sonar with a bit more realism. Not as a magical radar underwater, but as a set of tools and skills for carving structure out of acoustic chaos. Passive sonar listens to a world that is never quiet. Active sonar illuminates that world at the cost of revealing itself. Both are limited by physics, by how sound bends, scatters, and fades in the sea. In the next episodes, we will look at what happens when sound does more than just reveal submarines, when it guides weapons, when it shapes tactics, and when the ocean itself becomes both battlefield and hiding place. For now, remember this: in the deep, you never truly see with your eyes. You draw maps from vibrations, probabilities from noise, and survival from the art of hearing what others hope you'll miss.